Greetings. Let's investigate a special category of differential equations called autonomous. The definition is actually pretty straightforward. A differential equation of first order counts as autonomous if the derivative of the function equals something about just the function itself. No dependence on the independent variable. And of course, the variables don't have to be y and t. You just use whatever variables you're working with. But in many cases, we're talking about a function of time and some differential equation that doesn't depend on time at all. So these are also often called time-independent differential equations. And these tend to have a lot of practical applications. For example, population growth is one common example. If you're dealing with some population of individuals, p of t, presumably population changing as time passes, the rate of change in population is generally going to depend on birth rate minus death rate. And in a fairly simple model where we don't have to worry about things like limitations on growth, both birth rate and death rate tend to be proportional to population right now. For birth rate, presumably in any given interval of time, a certain percentage of the population gives birth. So the birth rate is going to be the population itself times some fractional birth rate. Likewise for death rate, presumably a certain fraction of the population dies every year, or whatever the time interval is. So death rate will be population times some fractional death rate. Subtract those, and note that we can factor out population, and just get population times some combined constant. That is then time independent. The rate of change in population depends only on what the population is right now and this constant. In a more complicated analysis, we might assume that birth rate and death rate could depend on time, maybe seasonality for instance. Another example of this is fluid flow. If you have something like fluid draining out of a tank. Let's say you have some tank of water with a drain in the bottom and water up to a certain level, draining out right now. The rate of change in the height, dh dt, is going to be proportional to the depth right now, the height right now, because the more height there is, the more pressure there will be at the bottom. And the more pressure there is at the bottom, faster fluid is going to flow. So the rate of change in height right now is proportional to the height right now. We can write that as a differential equation. dh dt equals some constant, presumably a negative constant because the height is decreasing, times h itself. And there are many other applications as well. Essentially, any time the rate of change of some quantity depends only on how much there is right now. A counterexample might be in any equation that does depend on t. For example, dy dt equals y squared plus 5 is autonomous. But let's say dy dt equals y squared plus t is not autonomous because it depends on time. One of the advantages of autonomous equations is that they can always be solved guaranteed in a certain way. If you just have dy dt equals some function of y alone, do you see what technique could always be used to solve this? Good thing to check first, can we separate variables? Note that this is just a function of y only, so if you multiply both sides by dt and divide both sides by that function of y, you end up with 1 over a function of y dy equals 1 dt. At that point, you've separated variables, so you can integrate both sides. So one of the neat things about autonomous equations is it's guaranteed to be separable. Separation of variables will always work. Of course, that's not always very practical because this 1 over f of y isn't always easy to integrate. So integrating this isn't always the best way to do it. It'll work, but it might not be an integral that's easy to do. However, one way that also works, one other form of analyzing these, is the direction field. The idea of a direction field will always be pretty easy for these because derivative depends only on y itself, not on t. So let's try drawing some direction fields for these. So if we want to draw a direction field for this differential equation, y prime equals 3y minus y squared, we might start by choosing some ty coordinates. Let's say when t equals 0 and y equals 1, for example. Let's say that's our initial condition, or just some point we want to analyze. We plug in 0 for t, there isn't any t. Plug in 1 for y, you get y prime equals 3 minus 1, 2. So that means at the location 0, 1, we're going to have slope 2. But notice that this didn't depend on t at all. If we change t, let's say we have 1, 1, the slope is still going to be 2. Or 2, 1, the slope is still going to be 2. So you don't need to worry about t values at all. If you just choose a y value and calculate the slope, it's going to be the same slope at that y value no matter what t is. And what this means is we don't really need the complete direction field. We could just take a look at, for instance, a single vertical cross-section of the direction field, and we'll know that the rest is going to be identical. And we can draw this in a certain way that's often called the phase line. The phase line is a very useful tool for analyzing any autonomous first-order differential equation. The idea is we're drawing essentially a single vertical cross-section of that direction field. And what we most care about is locations, that is y values. If you imagine this as a y-axis, we're looking for y values that make the derivative 0. So what derivatives, or what y values make the derivative 0? We can just set y prime equal to 0. Notice that this is factorable. We can factor out y. And it looks like this becomes 0 when y is 0 or 3. So we can just mark 0 and 3 as important points on the phase line. Y equals 0, y equals 3. We know that at those locations the slope is going to be 0. So we call those equilibrium. Equilibrium in the sense that the slope there is 0. So if you start at that y value, you're just going to stay at that y value forever. In fact, on the graph of the direction field, that's just going to look like horizontal forever. Same thing at y equals 0. Slope 0. But what we really care about also, not just where it's 0, but also what's happening in between. For example, let's say we substituted 1 for y. We already found that when y is 1, the slope is 2. We don't really care exactly the value, but the important thing is it's positive. In this in-between region, the slope is positive, so that means y is an increasing function. Between 0 and 3, we've got an increasing function. On the other hand, if we used a y value larger than 3, let's say y is 1,000,000. 3 million minus 1,000,000 squared would be even bigger, so we'll end up being a negative value. In fact, anything above 3 is going to have a negative slope. That is, a decreasing function. Likewise, anything below 0, you fill in any negative number for y. 3 times a negative number minus y squared is going to be even more negative. So anything down here is going to be a decreasing function, negative slope. So this phase line is essentially a map of how the function's changing at any y value. Again, recall the definition is that the rate of change depends only on y itself. This shows what the rate of change is for any y value, grouping it into these three categories. And using that, we can further refine the idea of equilibrium. If we're exactly at 3, we stay at 3 forever, which is why it's equilibrium. But if we're near 3, let's say you're a little bit above 3, what happens? You get pushed back down to 3. Or if you're a little bit below 3, you get pushed back up to 3. So this is called stable equilibrium in the sense that if you're near there, you just get pushed back towards there. On the other hand, if you're near y equals 0, again, if you're at y equals 0, you'll stay there forever, so that is still equilibrium. But if you're a little bit above y equals 0, you get pushed further above. If you're a little bit below, you get pushed further below. So this would be an unstable equilibrium, in the sense that anything nearby gets pushed away rather than towards. So that would be the phase line. We've now categorized and identified all the equilibrium values, and we can now easily turn this into a direction field. We've already marked the equilibrium locations, y equals 3, y equals 0. In between, we've got an increasing function, presumably fairly weak slope near 0 and 3, and then steeper in the in-between zones. But if we're above 3, we're going to have a negative slope. Again, pretty close to 0 if we're near 3, and then steeper further up. Likewise, if we're below 0, we're going to have a negative slope, pretty close to flat if we're near the equilibrium solution, and then steeper as we get further away. You could also imagine this as just filling in the phase line, that single cross-section, then taking that single cross-section, copy, paste, 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 because any single vertical cross-section is going to be identical. And now that we've got this mapped out, the entire direction field, we can start drawing in some sample solution curves. For example, if we start off at 3, we stay there forever. At 0, we stay there forever. If we start off anywhere above 3, we're going to get something like exponential decay towards it. Anywhere below 0, it looks like we get exponential decay shooting down to negative infinity as the limit. If we're in between though, let's say we start off a little above 0, we get a weak upward slope, then it gets steeper, then less steep, and levels off again. So we get these logistic curves with two asymptotes. So that's the general idea there. We take a differential equation that's autonomous, identify the equilibrium solutions by setting y prime equal to 0, mark those on a phase line, figure out what's going on in the in-between regions, and then it's fairly easy to turn that into a direction field. Let's try out another example while we're at it. Here's another autonomous equation, y prime equals a more complicated polynomial, but I've written it in factored form from the start. Factored form makes it much easier to see where the equilibrium solutions are, because it's quite obvious to see that y prime is going to be 0 when y is 3 or 5 or 8. So let's mark those on the phase line. I've set up a phase line to scale with the direction field axis just to make things easier. So 3, 5, and 8 will be the equilibrium solutions. And we'll want to figure out what's going on in between those to figure out where it's going to be stable versus unstable. Instead of just plugging in a bunch of numbers between these though, it's often easier to find that out by graphing this entire function. Recall we were calling this function f of y. So this whole thing is f of y. If we graph y versus f of y, it often becomes much easier to see where it's increasing versus where it's decreasing. So let's try a quick sketch of that. Putting y on the horizontal axis here and f of y, that is this whole polynomial, or whatever the function happens to be, on the vertical axis. We already know the important points are going to be y equals 3, 5, and 8. So let me just mark those on the axis here. And we know that the polynomial is going to hit 0 at those points. 3, 5, and 8. And you could try plugging in some numbers in between these to figure out where this is positive or negative. But if you remember some of the basics of graphing polynomials from maybe an earlier math class, this becomes much faster. We know, for instance, that we have, this is a 1, 2, 3, 4th degree polynomial. So presumably it's going to look something like this, or something like this. And in particular, it's got a positive multiplier, positive 1, as the coefficient on y to the 4th, the highest degree. So it's got to be going up to the right, and in this case up to the left as well, because it's an even power. So we at least know it's going to be going up in both directions here. You can also figure that out by substituting in some very large positive or some very large negative, or even 0 for y, and see what you get. For the in-between, the important thing here is that y minus 5 is being squared. So that location is going to look like a parabola locally. Whereas y minus 3 and y minus 8 are to the first power, so that's going to look more linear locally. That is, at 3 and 8 it's going to go through. At 5 it's just going to touch and bounce off, much like a parabola. So we can expect the graph to look something like this. That is the graph of f of y. And if you want more detail, if you want to know how steep it goes, or how deep it goes, or how high it goes, you can graph that on a graphing calculator or plug in some numbers and get more detail. But the important thing is we now know where f of y, that is the value of y prime, is positive versus negative. So we can parcel this out into this entire zone. It's going to be positive, sorry. This zone and this zone are both going to be negative. And then this zone is going to be positive because it's above the axis. So we're just listing out which regions, which categories or intervals are going to make y prime positive or negative. And then you can essentially take this y-axis, tip it sideways, and you've got your phase line. In the region where y is greater than 8, f of y is positive, so y prime is positive, so we have an increasing function. The region between 3 and 5, and 5 and 8, not including 5 itself, of course, has a negative slope, so that's going to be a decreasing function. And the region where y values are less than 3 is going to have a positive slope, so that'll be an increasing function. So if you've got the graph of f of y, it becomes very easy to figure out which regions are going to have positive or negative slope. And then we can quickly categorize the equilibria as well. At y equals 8, everything's diverging away from that point, so that's going to be unstable equilibrium. Y equals 3, everything's coming towards that point, so that's going to be stable equilibrium. And y equals 5 is kind of unusual. On the top, we've got values going towards it, so it looks stable. Underneath, we've got values going away from it, so it looks unstable. That mixed case there is called a semi-stable or half-stable equilibrium. Semi-stable equilibrium, or sometimes called half-stable. And that tends to happen when the graph of f of y has a vertex on the axis, where it comes up, from, let's say, from negative, hits the axis, and bounces back to negative. Or when it's coming down from positive, hits the axis and bounces off back to positive instead of going through. So that's our phase line, that's our categories of equilibrium points. Let's try graphing the direction field. At each of the equilibrium locations, of course, the graph is just going to be flat. At 8, 5, and 3, we're going to have 0 slope. And of course, that can continue forever. If you start at equilibrium, you just stay there forever. And then in between, let's say above 8, we're going to have a positive slope, presumably fairly weak just above 8, and then steeper as we go higher up. But as usual for autonomous equations, it does not depend on t. We've got the same value if we go to the left or right. Or if we're below 8 but above 5, we're going to have a downwards slope, a decreasing function. Again, we should expect a weak slope near equilibrium, but maybe steeper in between. And again, if you have a more accurate graph of f of y, how deep it goes or how high it goes gives you an idea of the steepness at each of those values. For instance, if you happen to know the maximum or minimum value of f of y, that tells you the y value where the slope is going to be steepest. Likewise, between 3 and 5, we know it's a decreasing function. Again, presumably fairly weak near equilibrium, and then steeper more in between. And then everywhere below 3, we've got an increasing function, getting steeper as we're further away from equilibrium. So as a very good sketch of the direction field, we've got this. Without too much effort, we just graph f of y, use that to make the phase line, use the phase line, especially the equilibrium values and the in-between signs, positive or negative slope, to draw a quick direction field. And then we can start sketching in sample solutions. Equilibrium, of course, will always just be a flat line. In between, or above 8, looks like we've got something like exponential growth, shooting off to positive infinity. Below 3, it looks like we've got something like exponential decay, approaching 3 as an asymptote. In between, it looks like we've got some logistic curves diverging away from 8, getting steep, but then flattening out towards 5. And likewise, between 3 and 5, a similar sort of case. Diverging downwards away from 5 and flattening out towards an asymptote of 3. So this is what we can expect those solution curves to look like. And we can even predict the end behavior and categorize everything. it looks like if the initial conditions are anywhere between 5 and negative infinity, all those initial conditions lead to converging towards 3. Any initial conditions between 5 and 8, all those initial conditions converge towards 5. Anything where the initial condition is greater than 8 shoots off to positive infinity. So this is a very useful tool, this idea of drawing the phase line and then the direction field. Very useful tool for figuring out what are the equilibrium values, what's going on between them, what kind of equilibrium we're talking about, and then sketching the direction field to figure out what shape the solution curves are going to be, and usually, most importantly, their end behavior. What happens to these solutions as t goes to infinity. So those are some very useful tools for your mental toolbox for dealing with any autonomous equation. Give that a try with some more practice problems, and I will see you next time.